Alright, hello there. Today we'll be presenting our new idea, Flight Sight, a new automated inspection of airport runways.
We define our problem based on the need to reduce airport loss of revenue from the closing of runways for manual inspection. Our goal is to collect the same data as an inspection team using a UAV to survey the runway from above. Our mission design is completed by our team, who reports to the stakeholders, who could be governments, airports, civil engineering firms, or inspection agencies, and we assume that there is a pre-programmed flight path for the UAV generated by the customer, and that the data analysis is performed by a ground inspection team.
Our overall concept is to use a drone that will gather conditions on a runway and relay this information back to a ground station. The predetermined flight path will be made by the operator, and the overall operation time of this drone will be about 8 hours. So we'll be using our drone to assess runway damages, and that'll determine where runways need to be maintained more properly. We can also identify fuel and fluid spills from aircrafts, and also find fluid leaks from other above ground pipe systems. In addition to all this, we can also map a large 3D area, which is the entire runway, and see where anything wrong is happening.
So our top level requirements for this UAV are to be able to gather data on the same types of problems that inspection teams would look for, such as the location, presence, size, and color of any non-uniform cracks, glass beads, lights, and so on. The maximum altitude would be 65 meters, and it must remain stable in order to gather sensing data. The UAV should be rechargeable with a power source that can last at least 4 hours of flight and sensor use. It will be able to store memory of sensor data. It will be able to land on its own. It can be programmed from the ground for a flight path, and it will have GPS capability, and it can safely house the components from potential weather damage during operation. Some examples of similar projects that use the same sort of technologies would be to scan buildings for structural instabilities after earthquakes, or to assess the damage to buildings that are caused by fire. Our project lifecycle begins with pre-phase A concept studies, where we will meet with airports and inspection teams to assess the system requirements and constraints on our UAV and develop a flight operation plan that conforms to FAA standards. During this time, we will also establish the invested parties and stakeholders, such as the airports in which we will establish these UAVs. We expect this phase to take about 3 months, and it will end with a mission concept review, where we propose the final product to our stakeholders. From there, we'll move on into phase A, which is our concept and technology development phase, which should also take about 3 months. From there, we'll make research into design choices, such as a purchase of LiDAR system versus in-house manufacturing. We'll do a cost analysis there, and the definition of the remaining sensor systems needed, a weight estimate, and the UAV size estimate. This will allow us to make a semi-final cost estimate for our presentation to stakeholders. We will close out this stage with a system requirements review for all the subsystems and the system definition review for the final product. From here, we'll move on into phase B, which is our preliminary design and technology completion stage. This should take about 6 months and involves the completion of the software development for sensor data storage and output, as well as the software for the pre-programmed flight path along the runway. We'll also include a flight test of the motors and propellers with an estimate of the final weight of the UAV in order to make sure that it meets the flight requirements. We close out this stage with a preliminary design review to make sure that all components of the product meet the initial requirements. After this, phase C, final design and fabrication, will be shorter at only 2 months. During this stage, we will integrate the developed software for scanning and flight path following into the final UAV design, and perform field tests of the sensors and flight software, gather data, and work to improve the integration. We'll follow this with a systems integration review for the software and the flight tracking, and then finalize the design in the critical design review. Once the critical design review is completed, we move into phase D, which is system assembly, integration, test, and launch. During this 1-week period, we will perform the first test on actual runways during airport operation. After this, we complete a post-launch assessment where we review the data from the sensors and compare it to normal inspections and suggest improvements to the software development. Once the design is finalized, the project will move into phase E, which is an ongoing operations and sustainment stage. During this time, we can make improvements to the manufacturing time and cost of the UAVs in order to make them more attractive to potential buyers and allow them to expand into other airports. We'll also update the software to account for issues and additional needs of other airports. And we can also explore additional applications of this UAV technology for surveying, such as the structural analysis of large projects such as bridges and buildings. The chosen system architecture begins with programming a flight path into the UAV and allowing it to scan along the route to gather data on the runway and return to a docking station, where this data is reviewed by airport personnel. It will then be sent out again at regular intervals to continue monitoring the runway and gathering data every time. FlightSight's product breakdown structure is divided into components necessary for the UAV operation and components for the docking station. The UAV is divided into a structural assembly that will house navigation systems, sensor systems, an electrical assembly, motors to power the propellers, and a hard drive for sensor storage. The docking station will incorporate a structure which connects to the UAV, data transfer points to take data off the UAV's hard drive and store it in the personal computer, as well as an electrical wall plug in order to charge the UAV battery between flights.
Our main UAV has multiple sensors that connect to the motherboard and feed information to it. The battery powers the motherboard and the hard drive, while the hard drive stores the motherboard's information. Our navigation system controls our motors through the motherboard, and our entire UAV is held together by a frame. All our data is transferred through our hard drive to the docking station by one key drone connection hub. The docking station will have a memory box that will transfer data to the ground stations, and have a USB port that will connect straight to the hard drive of the drone itself. The electrical assembly will connect to a wall, and the entire docking station has one big structure that will hold the UAV up while charging.
FlightSight's work structure is broken down into production for creation and execution of manufacturing plans, research into FAA regulations and optimum sensor layouts, management to develop schedules, reviews, and budgets, systems testing for the development, testing, and selection of a design, and logistics for communicating with airports and developing a closeout plan. FlightSight's operational flow is divided into flight preparation, obtaining of sensor data, and then transferring of data into a personal computer. During the flight preparation stage, the sensors are calibrated and the pre-programmed flight path is uploaded to the UAV from the docking station. The flight is then begun, and the data collection stage uses all sensors to store data to the hard drive. Once the flight path is completed, it returns to the docking station, at which point data transfer begins and the sensor data is put into a computer for analysis. The requirements for the structural frame are to hold all sensors while ensuring they have a clear view of the ground and making sure that all electrical components are fully protected from weather effects. It must also prevent overheating of electrical components and incorporate space for the motors and propellers for the UAV. In addition to the frame, the structure will also incorporate a motor and propeller system to produce more thrust than the weight of the UAV and landing gear that prevents the UAV from being damaged upon landing. The navigation system must keep the UAV stable and provide GPS accuracy along a pre-programmed flight path to an accuracy of 4 horizontal meters, which is the same as US civilian GPS accuracy. In addition to temperature requirements, the electrical systems must be able to have enough storage to contain the flight path and sensor data code. The battery must last for 4 hours of charge and 750 cycles of operation, and the hard drive must be able to store at least a terabyte of sensor data. The subsystem requirements for our sensors include a photometer, spectrometer, LiDAR system, altimeter, camera, and smoke detector. All of these sensors must be able to function accurately at the scanning height of the UAV. The technical performance parameters that will be monitored throughout this project are the mass, power, and speed of the UAV, the optimal dimensioning altitude for the sensors, as well as the budget and development time of this project. The margins for these parameters begin at 50 to 30% in pre-phase A and are gradually shortened by phase C to 25 to 15%. By phase D and E, the operation parameters should be shortened to approximately 0% margin, whereas power and maximum speed can remain at 5% to 15% as they are not necessarily required for performance of the UAV.
To verify our structures and sensors, we will weigh it and we will stress test it to make sure that it is within optimal parameters, and we will also temperature test it as well. To verify our electrical navigation and memory components, we will flight test it for navigation, we will do quality control checks to run its electrical components, and we will check data units by verifying its operational speed.